Good afternoon, everyone. Thanks for attending the seminar today. It's my pleasure to introduce Urmish Thakker, who is a deep learning researcher at Samba Nova Systems. Before joining Samba Nova, he worked with ARM Research, AMD, Texas Instruments, and Broadcom. His research has focused on efficient execution of neural networks on resource-constrained devices. His work has led to patents, publications, and contributions to various products across multiple companies. Urmish completed his master's in computer science from University of Wisconsin-Madison and bachelor's from BITS Pilani in India. Thank you so much for joining us, Urmish. The floor is yours.
Thanks, Hadi, for the introduction, and good afternoon to everyone who's on the call today. Today, the topic of my talk is going to be pushing the limits of LSTM compression. So hopefully by the end of this talk, I hope that people learn three things. Firstly, to enable an era of IoT machine learning, we really need to invent technologies that can take a large neural network application and compress it and sort of push it into a smaller device with a smaller memory footprint. Hopefully, you would also see that traditional compression technologies do not allow us to get there, and the two new compression technologies that we talked about, Kronecker Product and Doped Kronecker Product, can be a potential solution, if not niche, it should not be niche to these problems. So let me sort of scope out the problem first as to why we were pursuing this research. So this research was done with collaboration when I was at ARM's ML Research Lab, and ARM really cared about IoT machine learning, that is machine learning on IoT devices. So the aim of the project was to develop compression technologies for ML on kilobyte budget, or rather the aim was to understand if we can push applications on a kilobyte budget. And we realized that for the applications that we cared about, we really had to have a technology that can really push the limits of compression by a factor of 15x or more. So if an application took 15 MB, after 15x compression, it will take 1 MB. The application that my work specifically focused on was LSTM networks that are popular to process time series data and for natural language processing applications. And these LSTM networks generally have these very large dense layers or fully connected layers, as they are called in neural networks. So first, let us understand why do we need a large compression factor and how does that help us? So on the left-hand side of your screen, you see three different applications: keyword spotting, human activity recognition, and a chat application. So keyword spotting application is the one that you use to talk to your Alexa or any home device. So when you say, Alexa, play this music, or Alexa, turn on your light, that's keyword spotting application. Human activity recognition is basically a device that allows you to determine whether you are running, you're walking, you're sleeping, or doing any other activity. And the chat application basically is a proxy for an application that allows you to have a hands-free communication with either your smartwatch device or your mobile device. And so, sort of these communications are slightly longer than what you would see in your keyword spotting application. Now, all of these applications are critical from an IoT point of view because A, they need to be deployed universally, and also they need to be generally running in an always on mode. So both requires running these devices onto a smaller platform. Because if you want an application to be deployed universally across all devices, then you want to support devices that are cheaper. What that means is that you want these applications run on devices that are going to be slower and possibly have lower memory footprint. And you also want to run these on a smaller device because you want these applications to run in an always-on fashion. And what that means is that in a battery constrained scenario, you do not want these applications to consume a large amount of memory. And that's what a large compression factor allows you to do. So you take a 1.5 MB human activity recognition application, compress it by 20x, and now you get an application that is of size 75 kilobytes. So earlier you might be running this on a large scale microcontroller, but with 75 kilobyte budget, you actually can run it on a say Cortex M0 or maybe an M3 sort of a device, which is much smaller, much more energy efficient, and very, very cheap. The same thing with the chat application, where you can After 25x compression, instead of running on your phone, you might be able to run this on a high microcontroller or probably your smartwatch application. And in case of keyword spotting, after that amount of compression, you enable this application to, in fact, be hard coded into your hardware accelerator if need be, if that's the power consumption point that you are targeting. So for all these three applications, large compression factors really does enable us to explore very exciting new opportunities. So hopefully by now you're convinced that large compression factor is good. So at that point, we were thinking whether traditional technologies or whether the traditional way things are done in a neural network for compression point of view work. So neural networks consist of multiple layers, and each layer, the main sort of workhorse or the main thing that takes up most of the area or budget, memory budget for the application are the weight matrices in those layers. So the two ways to reduce the amount of memory footprint of a neural network that were popular at the time this research was being done was pruning and low rank matrix factorization. So in pruning, what you do is that you take the weight matrices of a neural network and set certain values to be 0. The values that are set to be 0 are determined based on some sort of saliency matrix, which would either determine that maybe the magnitude of the weight, if it's below a certain threshold, remove it. If the weight doesn't contribute to, say, some sort of the cross entropy loss that much, remove it, and things like that. The saliency metric could be defined in n number of ways. But the key idea is that the saliency metric would determine what weights are not important, and that those weights would be removed. And eventually, over training, you would recover the lost accuracy because of the lost weight. Now, in a matrix, if a lot of values are 0, you can store them in a specialized structure called CSR and actually get compression out of it. So a matrix with a lot of zeros will actually take up lesser area than a matrix without any 0 in it. The next way of compressing a neural network is low rank matrix factorization, or LMF. In case of LMF, you take a larger matrix and break it down into two smaller matrices. So people who are familiar with SVD, this is basically SVD, but the way it differs in neural networks is that you are training aware. That is, you instantiate your weight matrices in a neural network using W and H instead of V, and you learn W and H during the training phase. So during storage, because you don't store V and we store W and H, the number of parameters required to store the neural networks are less. Now we took these compression technologies and applied it to the three applications that we talked about previously. And what we observed is that these traditional technologies did not work for us. For human activity recognition, you saw almost 7 to 3% loss in accuracy. For keyword spotting, you saw almost 2 to 3% loss in accuracy. And for language modeling, which is a chatbot application that we talked about, and in case of the chatbot application, the accuracy is measured using something called as perplexity. And in case of perplexity, the lower value is better. So the baseline perplexity, that is when there is no compression, was 78.3. And after pruning, after 20x compression, you get a perplexity of 88.5. 78.3 being lower than 88.5 is actually the better value. And as you can see, both pruning and LMF lead to significant accuracy degradation. So then the traditional compression technologies didn't allow us to get where we wanted to. Yes, they do compress the neural network by the amount that we want, but the significant accuracy loss that we see effectively renders the application useless. So that the quest became to understand how could we solve this problem, or what tools could we use to solve this problem. And that's where we ran into Kronecker Products. Now, before I get into why Kronecker Products, I sort of wanted to take a step back and explain what Kronecker Products are to people who might not be from a linear algebra background. So Kronecker Product is a block-based matrix multiplication algorithm. If you have a matrix A of size M cross N and a matrix B of size P cross Q, then you get a larger matrix C of dimension MP cross NQ using Kronecker Product. And the way you get that done is that you take each scalar value in A, scale the matrix B, and stick it into different quadrants of the larger matrix C. So instead, so the larger matrix has a dimension MP cross NQ, so that requires Mn PQ number of parameters to express itself. But because this larger matrix was constructed using this fixed structure from these two smaller matrices, now it requires only MP plus NQ number of parameters to store. If this seems slightly convoluted, hopefully this example and a walkthrough of this example would make it a bit more clear as to what Kronecker products are. So you take one. So here you have a matrix C of size 4 cross 4 that is expressed as a Kronecker product of two smaller matrices A and B. You take the first value, value 1 from A, scale the matrix B and stick it in the top left corner. You take 2, scale the matrix B and stick it in the top right corner. You take 3, scale the matrix B and stick it in the bottom left corner, and similarly the bottom right corner. So effectively, a matrix that should have required 16 parameters to express itself is expressed only using 8 parameters, and you get 2x compression. And the amount of this compression increases as the size of the matrix increases. So suppose your matrix C is of dimension 256 cross 256. So your and you express it using A cron B, where A is of size 16 cross 16 and B is of size 16 cross 16. So instead of 256 into 256 number of parameters to express C, you only require 256 plus 256 number of parameters, each coming from A and B. So that's 128x compression to express the matrix C. And the larger the matrix becomes, the more compression that you get. Now, just because a compression technology gives you more compression doesn't mean that it'll give you good accuracy after compression. And then we saw that with pruning and LMF. The thing that sort of caught my attention, or sort of caught our attention of Kronecker products, was this property of rank preservation. So for people who are not from linear algebra background, the rank of a matrix is a notion of the expressibility of a matrix. So the more expressible, I guess a more offhand notation would be, the more expressible a matrix is, the better it is for a backpropagation algorithm in a neural network to figure out a local minima that gives you the best accuracy. If that's unclear, then you can think of rank as the amount of vocabulary that a person understands in a language. And the bigger the rank, the more the vocabulary, the richer the understanding of the language is, and the richer the communication skills. And that could be sort of used as an analogy to understand the relationship between rank and accuracy. Now, this analogy of more rank and more accuracy is not always true, but it can be said it is generally true. So the Kronecker products can have large amount of compression and preserve sometimes all of the accuracy. So that motivated us to explore Kronecker products as a use for compression tool in neural networks. However, when we started doing that project, we realized there are multiple challenges in terms of what design choice do we need to make. Specifically, remember, with the Kronecker products, all we want is that the smaller matrices multiply to a larger matrix to a dimension that we want. So the dimension would be chosen as a hyperparameter based on the application that you have. And these are basically the number of inputs and outputs of a neural network layer. So when the number of inputs and outputs are fixed, the dimension of those matrix of that layer is fixed. But even there are going to be multiple choices in terms of Kronecker factors. We saw C being expressed as a Kronecker factor of a Kronecker product of 2 Kronecker factors. In this case, we see C and A1 and A2. But C can be also expressed as a Kronecker product of 3 Kronecker factors or 4 Kronecker factors or n Kronecker factors. In fact, as the number of Kronecker factor increases, the amount of compression increases significantly. So the question becomes, how do we choose the number of Kronecker factors? And instinct would be that we want more compression, so we just go for this last option where we choose n number of Kronecker factors. So what we did was to launch a bunch of experiments across these different design points for a small toy application, and something interesting came out. And the thing was that as the number of Kronecker factor increases, the backpropagation becomes harder because you run into vanishing gradient issues. And once we saw the theoretical evidence, we went back and looked at all the backpropagation equations that happen with a large number of Kronecker factors. And we realized, yes, theoretical evidence backs this experimental evidence. So when backpropagation equations travels through these chain of smaller matrices, they get dampened at every step, leading to vanishing gradient issue. This is somewhat similar to what happens in a very, very, very deep neural network, but the solutions that exist for very deep neural network could not be applied here. So the idea then became, okay, so the design space became a little simpler, right? We need to reduce the number of Kronecker factors that we have. But what is that reduced value? Should that be 2? Should that be 3? Should that be 4? So again, we had choices. So the next problem that we encountered is, how does inference happen in a neural network when you express a matrix as a Kronecker product of 2 smaller matrices? So I talked about a challenge again in the previous slide, but I didn't give you a solution. But the solution to this problem actually solves the previous challenge also. So yeah, once you get there, hopefully it becomes clear. So in a neural network application, you can divide the development of a neural network application into two phases. One is the training phase and one is the inference phase. Now, generally for most applications, when you deploy that neural network, you only see inference happening. I know there is a lot of work happening in federated learning, which Hadi and his group are doing, and which look at learning on the edge device. But for the purpose of my work, we're only targeting inference. So inference basically means when you have an input coming in, doing some sort of prediction on top of that. In case of an LSTM network, the main computation that happens during inference is the matrix vector product calculation. So your matrix represents the layer, your vector represents the input to that layer, which could either be coming from the previous layer, or it could be your audio stream data, or some sort of sentence embedding data. Now your matrix C is expressed as a Kronecker product of two smaller matrices. Remember, the matrix C does not exist in its full glory. It's expressed as a Kronecker product of two smaller matrices and exists as such. So then how do you do inference? So one solution is you expand this matrix into a larger matrix and then do a matrix vector product. But by doing so, you become slower than the baseline network, right? Your baseline network was only doing CV, but now you're first doing A cron B and then you're doing CV. And for a lot of these applications, being real time is important. So increasing the inference runtime is not a solution. However, there is enough work that was done in linear algebra that showed that if the number of Kronecker factors is reduced to 2, you can actually do matrix vector product calculation without expanding the smaller matrix into a larger matrix. I won't get into the details of this linear algebra math, but if you go read the paper, I point out the references that have very clearly and easily explained why this is happening. So basically, by restricting the number of factors of 2, we have solved both those challenges that we talked about previously, the runtime issue and the vanishing gradient issue. So good. Now we sort of have restricted our design space for neural networks using Kronecker product to 2 Kronecker factors. Right, and then this slide sort of summarizes the fast inference again, saying that if we use the linear algebra trick that we talked about previously, during inference, the number of mathematical operations that are required to do inference on a compressed network using Kronecker products is reduced by a factor of 8x when the matrix is size C, when a matrix of size 256 cross 256. All right, so we are at a point where we have a reduced design space with 2 Kronecker factors, but even then there are going to be multiple choices. So remember, all we want from the Kronecker factors is to create a matrix C of a dimension that we want. So if a matrix C is of dimension 256 cross 256, then we have 2 different choices. In fact, we have more than 2 different choices, but you only see 2 here on the screen to get to that matrix C. Either your A and B each can be 16 cross 16, or your matrices A and B both can be of size 6, can be of size 2 cross 128 and 128 cross 2. So then the question becomes, what do you use to compress the network? Do you use this methodology or do you use this methodology? And one quick sort of comment could be that maybe you use a technology that you use the hyperparameters that give you maximum compression, but both of them actually give you equal amount of compression. So again, this question becomes a question of choice, and we need to find a way to approach a solution to narrow down the search space. And this is where the rank property becomes equally interesting. So what we observed is that if we equally distribute the dimensions of C across both A and B, we both get maximum compression and maximum rank. And the algorithm to do that is based on prime factors, which again, we point to the paper. But for the purpose of this talk, I'll limit this to the conclusion that you need to equally divide the dimensions of the larger matrix C amongst the A and B Kronecker factors. So to come back to this sort of choice again, you have your matrix C of dimension 256 cross 256. You equally divide this dimension 256 across A and B. The way you equally divide is that you take a square root of 256, that will be 16, and you provide the A with number of rows as 16 and B with number of rows as 16. The same thing you do with the columns of C, which is again 256 and again You divide A and B equally amongst the 256 value. And what that gives you is a rank 256 matrix, while the other path to get to rank C gives you a rank 4 solution. And again, if we go on the assumption that more rank is better, then this becomes a better design point than this. And just to sort of clarify, we do end up running ablation studies to sort of reconfirm all of the choices that we have made. But I won't go into the experiments or the results of those experiments here. And then you can read the paper for that. So great. Now we have a design methodology to compress a neural network using Kronecker factors. And the idea is to take a neural network and train it from scratch by replacing all of the weight matrices using those Kronecker factors. And if up until this point, it was slightly confusing why Kronecker factors are important, hopefully this slide sort of summarizes that. So you're taking a matrix C, you're decomposing it into two matrices A and B. If C is of size 256 cross 256, you're expressing it using A and B of size 16 cross 16 each, based on the methodology that we talked about previously. These matrix C initially had a rank of 256. We get, after decomposing it, we compress it by a factor of 128x and almost retain all of the rank of the matrix, or retain all of the rank of the matrix, in fact, after compression. And then this is the paper, which is this is basically a technical report combining a bunch of papers that has been published across journals and workshops, sort of talking about the methodology to compress a neural network using Kronecker products. So hopefully now you are excited about Kronecker products. If not, the walkthrough to the results would actually might motivate you more to think about things from a Kronecker product point of view. So we compressed 4 different applications: keyword spotting, human activity recognition, and image recognition. And each of these applications are different number of parameters and are at different design points in terms of the size of the application. But all of them are proxies of some important IoT applications that we care about. We evaluated 4 different compression techniques. One was Kronecker products, other 2 was pruning and low rank matrix factorization that we talked about earlier. And the last is small baseline, which is basically a test to see if your neural network was over parameterized. And then basically you take a large neural network and trim it down by reducing the sizes of the layers. And for all of these networks, we compress them using 4 different compression technologies, training them to the good accuracy point. And then we took these compressed networks and run it on a high-key 960 embedded development board to get actual wall clock inference runtime. And what we see is that Kronecker products are generally the de facto winners when it comes to ISO compression comparison at those particular compression points. So if I take the keyword spotting application, if I compress it by 20x, pruning LMF small baseline gives you significant loss in accuracy, while keyword spotting with KP compression only gives you 1% loss in accuracy. The runtime also improves. You get the runtime reduced from 26.8 milliseconds to 17.5. It's not as big a reduction as for other compression technology. So that is a trade-off that you need to consider. What do you care about more? A similar story exists for human activity recognition. We now compress it by 30x. None of the compression technologies are even near a Kronecker product. You get an inference runtime benefit, but again, there is a trade-off where the inference runtime benefit is not exactly as good as for the other compression techniques. MNIST and USPS are again giving a similar story. In fact, USPS is a good example because this basically is a benchmark that was developed by Microsoft Research, and it was developed especially for IoT workloads, and it was really well optimized in terms of number of parameters, and we were able to compress it further, giving a large compression factor and retaining all of the accuracy. So hopefully by now, at least looking at the presentation till now, you're convinced that Kronecker products at least works for IoT workloads. And by IoT workloads, I'm talking about small or smallish applications that are important in the IoT world, which we want to push to even smaller devices. The next question that became we became curious about is that, can you actually compress a larger workload using Kronecker products? And then we thought we would be, because we were seeing such good results. So we wanted to just apply it to a larger workload. Specifically, we were curious whether we can compress a large natural language processing application. And these NLP applications are basically a proxy of chatbot applications. So we strongly believe that chatbot applications would drive the sales of device for the next generation of devices. So you would ideally want to talk to your mobile or smartwatch without having a touch interface. And what that means is that chatbot applications, if we are able to deploy them onto an edge device, might become very, very important. So the question became, what happens when you compress these large NLP applications using Kronecker products? So at this point, we were aiming to compress the application that we sort of started with is around 30 MB, so it is decently large, and the compress is using Kronecker products. So again, Kronecker products, as we said, as I said earlier, the larger the matrices get, the more compression that you get using Kronecker products, using the technology, using the methodology that I talked about previously. And because these applications had matrices of size 1500 cross 1500, the amount of compression was 338x. However, that compression came at a 27% loss in accuracy, which is basically you render the application useless. So as researchers, we became curious. What made Kronecker products work for small IoT workloads and did not make it, and what was the reason that it did not work for the larger NLP applications? And to understand that, we dig a little deeper to understand how basically the data flow happens, both in terms of forward propagation and back propagation in a Kronecker product. And that's where we started realizing what basically the issue was. So to walk you through what was going through our mind, let's go back to this example again. So here you have a matrix C of size 4 cross 4 that is expressed as the Kronecker product of two smaller matrices A and B. And again, we saw this example previously where we discussed that C is constructed from A and B by this element-wise scaling and then placing it in different locations in the C matrix. So you take one from A, scale B, stick in the top left corner, and so on you do to the other corners of the matrix C. So basically, what you have here is a fixed structure, right? All parameters in C are somehow related to parameters in both A and B, and one parameter in A or B influences multiple parameters in C. So in this case, each parameter in A influences or B influences 4 parameters in C. Now, what happens during backpropagation? Backpropagations don't follow this structure, right? Backpropagation always tells you individually for each parameter where they should move to get to a good minima. So what if, and this is basically a toy example just to understand what is happening, but say for an argument point of view, to get to the best accuracy you want for an application during training, you want this value in the larger matrix C to go from 2 to 4. So backpropagation comes back and says everything else should be 0 from a backpropagation update point of view, but this value too should go from 2 to 4. What happens then? Now remember, C doesn't exist, right? C exists in a compressed format, right? So the way you do that is you either change this value from 2 to 4, but this value influences all these 4 values, right? You took this 2, scale B, and stuck it in the top right corner. Or you change this value from 1 to 2, but when you change that one value, all these 4 values also change, right? So basically, even though you wanted one value to change, you end up changing more than one values from a backpropagation point of view. So basically, if you have this fixed structure that is created by Kronecker products, you get the goodness of high rank and large amount of compression, but you also get this negative benefit of not adhering to whatever the backpropagation signals are trying to communicate with you. So the question becomes, how do we solve this problem? So if you take a step back, the problem that we are trying to solve is that the problem that we are facing is that the fixed structure of Kronecker products does not allow a certain way of being, does not allow certain parameters to move around freely. Now, the thing is, we did not observe this in IoT workloads, but it's observed it in NLP workloads. So what made IoT workloads different from the NLP workloads? And the argument there could be made that for NLP workloads, the matrices, that the C matrix size becomes huge, right? For this application that we're looking at a 1600 cross 1600 sized matrix. So when the matrices become larger, each scalar in these smaller matrices has a larger influence on the matrix, right? So here 2 influences only 4 locations in C. right? But if C was of size 1600 cross 1600, then each matrix A and B will be of size 40 cross 40. Then each element in either A or B would influence almost 1600 locations in C, right? So that is where this problem was exacerbated in a larger NLP application, while in the IoT workload, we actually did not see this issue come out, right? We did in a way see this issue come out because even in spite of maintaining full rank, we were seeing slight loss in accuracy, which we never recovered. And then maybe the slight loss in accuracy could be attributed to the fixed structure. But with NLP application, the fixed structure led to a significant loss in accuracy. So the question comes back to how do we improve Kronecker products to work for NLP application? And what we basically wanted is to have certain parameters in the Kronecker product matrices to have these additional degrees of freedom that a Kronecker product structure does not allow. And the solution then, once we look at the problem, solution becomes very, very, very simple, right? So here now what you're seeing is that the matrix is expressed as a sum of two matrices. You have a matrix that is a Kronecker product matrix, which is A and B here, and you have another matrix that is extremely, extremely sparse, right? And remember, at the starting of the conversation, I said that if the matrix is extremely, extremely sparse, I can store it in a specialized format that takes up very, very, very less amount of memory space. So effectively, you are still compressing the network, right? You took the weight value in a neural network, and you have decomposed into two matrices. One is a Kronecker product matrix, which gives you maximum compression, and other is the very sparse matrix. And what that allows you to do is that it allows the backpropagation equations, or it allows the weight values to adhere to the request from a backpropagation signal. So if this value wanted to go from 2 to 4, and you were not able to change any of these values because they had an influence on the larger matrix, you can take that update and put it into this very sparse matrix. And then for people who have a background in classical machine learning, this is basically what a robust PCA algorithm does, right? It's very similar to that. And this combined or nude compression technology is what we called as Doped Kronecker Product, which is basically combining Kronecker products with pruning, right? And then we call it sort of Doped Kronecker Products as a sort of a hat tip to the semiconductor world, where sort of ARM belongs, where we use doping as a mechanics or as a technique to excite semiconductor materials to give you all the electronics around you. And that is basically what this sparse matrix is doing. It's giving enough excitation to the Kronecker product matrix to push it to the accuracy point that you want. So hopefully the idea of Doped Kronecker product is clear. Now that the idea is clear, let us look at how do we identify the locations where we want the sparse matrix to have a non-zero value, right? And these non-zero values will correspond to the values in the larger matrix that need those additional degrees of freedom. So how do you do this? How do you determine what locations should be non-zero? And again, we borrowed to sort of overcome this challenge. We just borrowed techniques and tools that were invented in the pruning domain to identify important weight values and then remove non-important weight values. So basically what we do is that we start with a weight matrix that is expressed as a Kronecker product of two smaller matrices, that is mcron, and a very, very dense matrix, that is MSP. Now this dense matrix starts off being dense, right? So right now the number of parameters to store these two is actually larger than the number of parameters required to store W. However, as training progresses, we use the tools and techniques invented in the pruning domain to identify values in the dense matrices that are not important and prune them away over time. And the hope is that as the training progresses, the backpropagation and these pruning saliency criteria would determine the locations in the Kronecker product matrices that need those additional degrees of freedom and populate them in the corresponding sparse matrix. So at this point, we realized, okay, I think have a traditional, we thought we had a training methodology that allows us to compress NLP using this new compression technology called Doped Kronecker Product. So we again took our chat application, whose accuracy is measured using perplexity. So again, for perplexity, the lower value is better. Now we took that chat application, compressed it using Kronecker products, and we got 338x compression as we had seen previously. So basically, that's another way of saying that basically your MSP matrix is completely sparse, or it doesn't exist, or the sparsity is 100, or there are no non-zero values, whatever way you want to view it. Because if this is 0, then basically what you only have is mcron, which is basically your Kronecker product compression. So your Kronecker product compression gives you 338x compression, but the accuracy or the perplexity degrades from 82 to 104. And then what we did is add 1% more parameters into this msparse matrix. So we reduced the number of the sparsity of msparse from 100% to 99%. That is 1% of the locations in the msparse matrix have non-zero values. And because we're adding parameters to the neural network, the compression factor reduces. The compression factor goes down from 338x to 100x. And this was, we thought was, okay, let's see what the accuracy of perplexity comes out to be. But when we saw the perplexity, we were actually quite surprised. The perplexity, in fact, degraded. So we are doing far worse than we were doing by just doing vanilla compression, using vanilla Kronecker product compression. And this again led to some confusion. Why is adding more parameters not helping us? Why is this intuition that we had built that adding this sparse matrix might be useful not working for us? To sort of understand that, we sort of wore our hats as ML researchers and investigators and looked at what generally ML researchers do, and that is look at the training curves. So you are again seeing here the chat application that we talked about, which had multiple layers of matrices of sizes 2600 cross 1300, and you start the training process by expressing this as a Kronecker product of two smaller matrices and a very dense matrix. What you see on the bottom of the screen is the curve of training perplexity versus training epochs. That is, the more number of steps that you train the neural network, how does the accuracy on the training set, or in this case perplexity on the training set, improves or degrades. And again, in case of perplexity, the lower value is better. So in an ideal scenario, the ideal training curve that you see is that of a decreasing curve, right? As the number of training steps increases, as you progress through your training, the amount of training accuracy should decrease. However, in our case, we see a very weird sort of a training curve. Our training perplexity decreases initially significantly. That is, we are getting very good at understanding this application and learning that application, but it starts increasing again after a certain point. So the question becomes, what is happening? To understand what is happening, we also plotted the sparsity curve, right? So basically, the dense matrix is turned into a sparse matrix over time, and this black line indicates how much sparsity exists in this dense matrix. So initially the value is 0, right? What that means is that this dense matrix is entirely dense. There is no zero value in it, right? All values are non-zero. Now over time, when you get around here, you see that the sparsity increases to 99%. That is, only 1% of the values in this dense matrix are non-zero. So basically, the increasing amount of sparsity correspond to the poorer training run of the poorer training, increase in training perplexity of the application, or rather decrease in accuracy of the application. This was again perplexing, right? This is not what we expected. We wanted this sparse matrix to support the Kronecker product matrix and provide those additional degrees of freedom that might allow it to express itself. However, what we ended up doing is that we ended up making the application worse by somehow making the minima that was being learned too reliant on the dense matrix. And when we removed all of these values from the dense matrix, we were far away from the minima that we wanted and never recovered. So this is what we called the phenomena, what we called as co-matrix adaptation. And again, looking back, we realized that co-matrix adaptation actually makes sense. So in its initial dense form, the Kronecker product matrix, the number of parameters that these two smaller matrices have is around 10K, while the dense matrix has around 4 million parameters. So when the neural network training starts, the Kronecker product matrices get around 10K updates, while the dense matrix gets around 1 million or 4 million updates, almost a couple of orders of magnitude more than the Kronecker product matrices. Now, because the dense matrix is getting much higher number of backpropagation updates than the Kronecker product matrices, what you see is that the minima obviously has to become too reliant on the sparse matrix. And when you take away those parameters from the sparse matrix, you run into the accuracy issue. So now that we understood the problem, again, the natural question was to ask us to how to solve this problem. Now, Basically what we wanted to do was to reduce the adaptation that exists between the two matrices, the M sparse matrix and the M cron matrix. So we looked at a few techniques from machine learning to do that. One was to apply some sort of a restriction on the sparse matrix. So what we did was to multiply the sparse matrix with a value beta and sort of minimized, tried to keep the beta value down using L2 regularization so that the impact of the sparse matrix is reduced. The other value is that you can multiply Kronecker product matrix with alpha and then reduce the value of M1 upon alpha so that alpha increases so that the overall weightage of the Kronecker product increases. Another simpler technique is to train these things using block coordinate descent. And what that means is that you first train the Kronecker product matrix and blocking all the gradients to the sparse matrix. Then you train the sparse matrix, blocking all the gradients to the Kronecker product matrix, and you keep doing this on a step-by-step motion. And all of these things incrementally helped us to get good accuracy. However, the thing that provided us the most accuracy benefit was a new regularization scheme that we invented, which we called co-matrix regularization. So to again clarify, all equations 1 to 2A and 2B with and without BCD actually helped us to get good accuracy. But when we trained using CMR, that gave us the best accuracy. So again, I won't go into the details of what CMR is. I'll encourage you to go read the paper. But at a high level, CMR is basically an adaptation of the dropout regularization that is popular in machine learning. But we are now applying dropout at a much finer granularity than it was applied. So you can imagine CMR as being somewhere in between weight dropout and your normal dropout as was invented in machine learning. So it's somewhere in between. And then it has these nice properties that removes co-matrix adaptation and gives you really good accuracy. And then this graph is a testament of the fact that Doped Kronecker product matrices trained with CMR regularization actually give you highly compressed networks at very minimal loss in accuracy. So this is just one of the results. There are other results in the paper also, but let me walk you through this particular results, and then other results will look similar. So here what you are seeing is a plot of perplexity score on the y-axis with compression factors on the x-axis. Again, because you're measuring perplexity score, the lower value is better. And with compression factor, the higher value is better, right? So overall, across these two axes, anything that exists in the top right, is the bottom right corner is actually better than everything else. So baseline exists here at 1x compression because it's not compressed. And what you see is that Doped Kronecker product is the only compression tool that allows you to compress the matrix by almost 25x with minimal loss in accuracy. So this was the previous state of the art. We are almost improving the previous state of the art by 2.5x. And we beat other popular compression tools and techniques that are used. So hopefully this has sort of excited you, or these results, you find them sort of exciting enough to go read the paper. And I do encourage you to read the paper for a lot more results and a lot more ablation studies to nail down why Doped Kronecker products work and then what makes it tick. But for the purpose of this presentation, I thought I would not go into too much technical detail and then just give you a high level overview. At this point, I thought I'll just conclude my presentation. Hopefully you enjoyed it, and hopefully you took away these things that you see on the screen. Hopefully you learned something about Kronecker products. You learned about what is the issues or methodology you use to compress a neural network using Kronecker products. You learned about Doped Kronecker products, why Kronecker products did not work, and then how do you make it work. And then you realize that Kronecker products can be used to compress a neural network by a large compression factor while providing hardware on a speed up on existing hardware using the software infrastructure libraries that we currently have, or the software stack that we currently have available to us. One thing that I didn't talk about in this presentation, but it's sort of available in the paper, is the fact that quantization is another compression technology that is used popularly amongst people in the compression domain. And we show that quantization is sort of orthogonal to the compression tools and techniques discussed in this presentation, and then we further help you benefit those neural networks. That's all I had for you guys today. Thank you for listening to me, and at this point, I would be open to taking any questions that you might have.
Thank you, Urmish. It was a very interesting talk.